Hey, how are y'all doing? If one of you unmutes and uses words out loud, I can then hear you.
Hey, good. How are you? The best area identification number.
Yeah, there's always that too. So yeah, I'm glad I can hear you because I don't have the headphones on. Maybe that'll be better. But yeah, I guess time to sort of like do the normal thing. Unless any of you has questions right before we start up. I was just going to start by maybe sharing a screen, which will take me a little while to do. Okay, cool. Under this, I do the share screen. Boom. And that guy. Okay, so well, that's not exciting. Let's do that. Okay, so yeah, normal stuff. And again, because I have it set up such that I can't see you necessarily, it'll be hard for me to sort of know if you have a question unless you literally do unmute. Or I guess if you type something in the chat, I'll maybe see that, but I'm not using my screen real estate to display those things. Maybe remind ourselves where we're at in the syllabus. It seems as though we're about just over halfway done with the class. So maybe another midterm's coming up, and so like yeah, we're right around here. Oh my gosh! At the end of the day, we will be 60% of the way finished with things. So yeah, just over half. And you sort of think the next exam's going to be coming up. It covers stuff we've been doing recently in chapter 4, 5, 6, and that was chill. 7 was interactions a little bit more challenging. We're going to do interactions today in a different context, quantitative interactions, and then a tool that our author stuffs into chapter 10. Indeed, it's useful in chapter 10, but a tool that I'd like to address earlier, the partial F test. That's the topic for Monday and the last topic before the exam is turned out open live for y'all on Wednesday of next week. And so basically think one more topic besides chapter 7 today. Uh, Monday's topic is the last thing on the exam. So you have like a full day of chill material because chapter 8 and 9 students tend to think, okay, got it. We've done this already before. Got it. I understand. Okay. And then, so not a stressful issue. And then you'll have plenty of time to develop some review questions before we spend some time next Wednesday on the review before exam 2. Then, right after class, we'll turn it live, and that will give you until midnight, well, 11:59 p.m. Friday and Friday the 17th to get the exam finished. Okay, so there we go. Then other administrative things. I think yesterday I was asked, hold on, where were the notes? And I apologize that I didn't upload the notes in advance. I was sure to do that before class today. And I apologize that, yeah, I wanted to have done it earlier, but yesterday, right following class, I had office hours for a full hour when there were a bunch of students there, and then another class, and then I had to run off to an appointment. So here you go. These are the notes for yesterday, just those few pages, plus today as well. And then
Thank
also,
you.
oh, yeah, no problem. I'm happy to do it. I just sometimes need help remembering the things. In these quick paced summer terms, like, yeah, it's easy to forget a thing because, like, they go twice as fast as normal. Normally, I have time to breathe between classes, and yesterday I didn't. And then today we're sort of talking about quantitative interaction. So, there's today's talk. Okay. And then also maybe 2 years ago or 3 years ago, same deal. And students from past classes have said, oh, yeah, it's nice to have across our group. Yeah, we all showed up, or some of us showed up at class, and some of us watched, the 2024 version, some of us watched the 2023 version. And so you pick up on slightly different things in lecture per se if you're watching it later on. And so across the group, everyone's in a better place. The homework problems are C and D. I'm sorry, homework CD, and that's from chapter 7 of the Graffin and Hales textbook. Let me know if that's okay with y'all, because if not, I can maybe be helpful there, but definitely out of the textbook directly is where we find those problems. And then the lab for today is this lab 3D, D because it's Thursday. And so you'll be working on this guy with your groups later. Okay, so that's it for administrative things I wanted to mention. Do any of you have questions administratively that you'd like me to address? Okay. As always, just interrupt if you do. What we did yesterday then was nominally in this topic of interactions. And so maybe I sort of move forward in the slides to quantitative interactions, but maybe going back a little bit. Essentially, we're saying there is, with a categorical case, you have, an average commute time. Then there's the effect of the route on average across the commute times. The average effective route is a few minutes more if you're taking Highway 1, or a few minutes less if you're taking Los Osos Valley Road. If you leave early, there's a benefit, a reduction in your commute time. There's a drawback if you leave late. There's even a minor benefit of leaving on average time. But this is averaging over all routes. These route main effects are averaging over times. We have this belief that indeed maybe there is a differential impact of one route over the other at different times of the day. And so, yeah, literally 2R24 plus the 2.33 plus the negative 1.75 if you leave at 6:30 in the morning. You also then, you would subtract off another 0.58 of a minute, and that's like 40 seconds. Okay, it's just subtract off another 40 seconds. Because the Highway 1 effect of plus 2.33 and the 6:30 effect of negative 1.75 don't themselves completely quantify what's going on. There's an additional negative 0.58 impact of the combination. So the benefit of taking, or I guess the benefit of leaving at 6:30 is even more if you're taking Highway 1 than if you're taking Los Osos Valley Road. Okay? So that was the categorical context. Categorical quantitative, what we found yesterday really is that the trend line is no longer one line. There's two lines because we got a categorical thing, or three or four. And indeed, we had multiple lines, and they were allowed to have different slopes. And so the interaction is really a test for, is the slope the same across my groups? And if the slope is noticeably different in at least one of the groups than the others, excuse me. Oh, excuse me. So yeah, that raises Zoom etiquette. If you're the one giving the class, yeah, and then you have to sneeze, should you mute? You're welcome to sort of comment now.
I wouldn't know. I've never hosted.
But when other people and then they mute to sneeze, do you think that's cool, or do you think those of us who don't bother, you think, oh, that was gross?
I think you can sneeze with pride.
Some people's sneezes actually, deserve pride. I don't think mine is one of them, but we'll keep going. Okay, so in this interaction between a categorical group and a quantitative variable, the slope of that variable changes across the categories. And yeah, there's a little bit of algebra involved. And like we said, you probably want to be careful to not center. The default GMP is to center things. We don't like that. So in the lab instructions, we said, please turn that off. There may be a benefit later of centering that we'll talk about. Not a big benefit, but a benefit. But for now, we say don't do the centering. Turn off the centering. Any questions about any of that from the recent past? Okay, so let's move forward into a new context, quantitative interactions. So what I'd love to do is to sort of go over this conceptually. Regression with two x variables fits a plane. Okay, I think I've got a picture. I don't have a picture of a plane, but basically, if you have two individual slopes, it says if you change this x and the other x is unchanged, there's a linear relationship between x and y. If one x changes and the other x doesn't, then we'd see, oh, look, the slope tells us how y changes on average. And if the slope of y's relationship to one of the x's is always the same, no matter what the other variable level is, you'd say you don't need an interaction. We're fitting effectively a plane. If you have a regression with two x variables, effectively we're saying our flat plane, and I'm trying to draw a flat plane here, if we could bend it a little bit so that way, on the right side it goes up and on the left side it goes down. So I'm imagining like this sort of slope. You can see as I go from the one side of the screen to the other, the slope would change. Or like would suggest this picture here, if we are looking at the relationship between x1 and y being up high, if x2 is quite small in value, okay, like at this end, you see the slope is pretty shallow. But if x2 is quite large, notice at the back end, the slope is quite steep. A bent plane could be done with an interaction, okay? So let's look at a situation where maybe, by example, we see the need for an interaction. And I've got data on corn yield in various counties in Illinois in a single county in Illinois as a function of both what year it was and the rainfall amount. And I'm trying to, again, make sure we present this in the very narrowest way possible, because then we have room for other stuff on the screen. Okay. Okay, whatever. Okay, I'm just going to do that and I'm going to be happy with it. Okay. If I were using Graph Builder, and I always recommend Graph Builder to start with. If you don't like pictures, maybe you're not going to start there, but I tend to start with Graph Builder because I see something from time to time that's interesting. Yield maybe depends on the rainfall level. We sort of would think that the more rain you get, the higher the yield. And that's sort of a curvy line. I don't love curvy lines. Maybe I could make it straight, in which case I'm thinking I'm happy, or maybe I could just remove it. In any case, what happens as the years are shown differently? And if I chose year as a color, we're going from blue early on in history through the gray to the bright red. Okay, and I'm seeing bluish is sort of a positive trend. Yeah? I see you all nodding along, playing a home game here. The reds are sort of flat, or maybe even with this one included, maybe even sort of like negatively slopes, and the gray is sort of in the middle. So blue is steep, gray is sort of flat, and red is flat. Maybe gray is a little bit positive, but I'm seeing a different trend. We could not just use color, but we could go with an overlay. And in this overlay, we're sort of saying, well, in different categories of years, like the first 8 years, 1890 to 1897, the next 8 years, the next 8 years, et cetera, group of 7 or 8 years at a time. And I guess if I turn on my trend lines, it maybe emphasizes things nicely, make them straight. Early on in 1890, we see blue positive. Then if we go to 1897 to 1905, it's that second color, this reddish color here. Again, well, we see it. Okay, sort of it's a little bit, starts a little higher and it's a little bit shallower. Blue is quite steep. Red is a little bit less steep. We go to green. Green is pretty flat. Purple also pretty flat. And then finally, 1920 to 1927, in the last 8 years, it looks as though there's even maybe a negative trend. What I'm saying is the slope seems to be different for the different years. Would you agree? I don't know. I shouldn't use those rhetorical questions in Zoom. I'm claiming that the typical class of students, when I say, does the slope seem to change across the decades? They all say, yeah, we see it. You all see it. We see it. The pattern is steep, less steep, less steep, maybe even negatively sloped. Okay. Certainly, we start off early on with one sort of a trend, and later on, it's a very different kind of trend. And systematically, the intercept seems to keep getting higher, and the slope seems to keep getting lower. It seems as though the intercept and the slope both are changing across the decades. The claim is we could fit a model that handles that. Okay, so let's consider our first model, the second model, and then the third one. The first model's yield depends on just rainfall. Let's go ahead and fit maybe I'll make that smaller. I'm going to go ahead and fit the model. Fit model is the way I'm going to go. Yield depends on only the rainfall level. And clearly you're saying you think maybe year does matter. We even did an analysis earlier this term where, yeah, year mattered. But for now, we're going to say yield depends only on rainfall. I click run. And again, getting rid of the things that we don't always want or need to see. But I'm going to go with R squared. I don't want to overdo it, but R squared and maybe my effects test and my parameter estimates, as well as the ANOVA. And it seems like the p-value is always 0.0122, 0.0. Yeah, it's because just one slope has 1 degree of freedom, okay, in the effects test. That's also the same thing as the 1 degree of freedom t-test for slope. And the question of, do any of the variables matter? Well, if there's only one of them, it's the same thing. So here's a model with just, okay, one x variable. Okay, I'm trying to show you enough of it that where you can rely on it, but refer to it back again. But let's do the other analysis, rainfall plus year, fit model. Recall is my friend. Okay, I just pre-populates everyone, but I got to add year in here as well, because I think that maybe across time, there's increases in the impact of irrigation or fertilizer, or, we got a combine harvester all of a sudden, as opposed to, no combine harvester. We're doing maybe a little bit better. Again, leaving the things that seem to matter that we're going to want for sake of comparison. The summary to fit, R squared seems to be a little bit higher than before. Okay. So we went from 16 to 30%. That's good. The ANOVA, still says at least one of the variables matter. And we know it's gonna, because rainfall mattered. But now we're saying at least one of these two variables does matter. My slope tests, which are like adjusted sums of squares, basically say the same thing as my effects test, the adjusted sums of squares. Again, 1 degree of freedom of adjusted sums of squares or effects tests correspond exactly to the slope tests. And if you're wondering for fun, under estimates, had we done sequential, we would say, does rainfall matter? We'd say, yes, it does. And then above and beyond the effect of rainfall, does year matter? We say, yes, it does. But the fact that our sums of squares, sequential and adjusted, are different says we don't have orthogonality, which you rarely have in the context of non-experimental data. Okay, so second model, we're doing better. What if we include the interaction term as well, the rainfall year interaction? How could I do that? You already know, because you've done the interactions already. Recall, but I want to take year here and rainfall and cross them, the year rainfall interaction, if you will. And again, I've got the whole thing, and I'm going to sort of boil it down to our things that we like to use for the sake of comparison. And so move it down a little bit, and damn it, I did one thing that I didn't want to do, and that's good because I will now be able to emphasize it. Okay, so again, R squared was 30% if we had both X variables. Now, if we have both X variables plus then the interaction, it's like 50%. We have a huge benefit. We're explaining a lot more. Across any of the three variables, heck yeah, something matters. My adjusted sums of squares or parameter estimate t-tests say, yeah, all matter. My effects tests say, yeah, they all matter. If I had done sequential tests, I still think this makes sense. I actually like the sequential test. Well, if you have an interaction, a sequential test and later for the interaction makes a lot of sense to me. So let me try it. A rainfall, do we see a benefit of rainfall? Yes, it's better than nothing. In addition to rainfall, does adding in year help us? Heck, yes, it does. And above and beyond rainfall and year, does an interaction allowing the slope for the rainfall trend line to be different across the years, does that seem to help you as well? And the answer is, heck yeah, you need that. I would say the slopes are noticeably different across our groups. Any question about how you fit the model? Or the things we just went over? Okay, so what I'd like to do is to sort of just say our prediction equation. We're going to do some algebra. My profile graph, my profile plot. Again, that's nice to do. Let's do that next. What I want to remind you of first is, remember when we did the fit model? And I said, okay, I just clicked run. Isn't it just tempting to say, okay, yeah, now we run? Because like we did all the settings we need to do. I had forgotten that the center polynomials is something we don't love. It's actually not bad, but I prefer to not center polynomials here for quantitative interactions. Again, maybe we'll suggest a place later when indeed centering polynomials could be good to do, but in general, we don't bother with centering the polynomials in this class. I want to deselect that. I click run. And again, maybe let's compare it to the centered polynomials version of the same output. And again, looking at the same exact portions of the output. So turn on effects test and turn on sequential like before. And so row by row or item by item, let's do a comparison. R squared, the same. Not centered, centered. You can tell that it's not centered because I've got year minus 1908 and rainfall minus 10.78. Literally, this is year minus the average year and rainfall minus the average rainfall. And that's the thing we're multiplying together. Over here, we're just multiplying year by rainfall. And I think that's easier to work with. Our ANOVA, the analysis overall, I mean, R squared's the same. The ANOVA itself is the same, so I'm thinking I'm fitting the same models. My parameter estimates, well, it does seem as though we have a bit of a difference here. The intercept is like negative 2047. It used to be negative 239. That's awkward. But this the rainfall interaction, like a 0.08781, it seems as though only the interaction slope is the same, and all the others seem to change. Frustrating that we have this one and this one. Use the non-centered if in doubt. What about the effects test? The effects test down the line. Oh, hold on. Different. Different. Oh, that's awkward. That's awkward. They're different, and oh no, they are the same. The last one's the same. So the effects tests again are adjusted sums of squares. What about sequential? Sequential is a little cleaner here. Is rainfall helpful? Yes, it is. Same as before. Is adding in year better than not? Yes, that is true. And then is adding the year rainfall interaction helpful? Yes, it is. So the sequential procedure gives you the same exact testing whether you whether you center or you don't. So it seems as though in many ways we're fitting the same model. It's just algebra that we have to deal with here. Okay. I want to sort of maybe let's do the algebra first. And I want to key off of just these estimates here. So I'm going to make sure I have the estimates shown still. but I now have the whiteboard I could work with. And I got way too many things. Okay, so let's close them all except for the thing I need. Okay, so what I want is shown over here off to the very left, and let's make sure I have the pen. And I'm going to circle the numbers that I'm going to refer to. Okay, so what I have here is the following. The yield, y, and let's go with the pen version, not the erase version. My predicted yield is and I'm going to sort of go with a little bit of rounding, but maybe more than you really would want to do. 2047.0. Okay, and then I'm going to have plus 168.27 times then the rainfall level. And it looks like I'm going to run out of room, so I'm going to go down to the next line. Plus 1.085. I'm going to go 8545. Okay, yeah. 1.08545, yeah. Times then the year. Minus 0.08781 times then the rainfall level times then the year. Okay, now that I've moved or gotten the numbers written down, I'm going to move them off to the side because we don't need to refer to them at the moment. Okay, so what we have here is our model written down in purple, and let's consider two distinct years at which you might want to calculate the slope. And I'm thinking, what if the year is, say, 1890? And I might need a little bit of calculator help here, but I've got y hat is negative 2047.0 plus then 168.27 times the rainfall level plus 1.08545 times the year. Oh, but the year, we know the year. So I'm going to sort of go back a little bit and say, well, times 1890. Okay. And then I'm going to minus out 0.08781 times the rainfall level times then 1890. Maybe if I move this even further off, it will be less cluttery. Okay, good. And I've got my 1890 circled in one place, so maybe I should just go ahead and remove that. Okay, so what I have here is four separate terms, but two of them have rainfall in them, and two don't have rainfall in them. So I'm going to underline the things with rainfall in them. And the other things I could add together. And so let's collect like terms. And so maybe I'm going to write this down here. Actually, let's do it over here. Ha! I can do it this way. Save some time. Minus 2047.0. And I'm going to go with the other thing that doesn't have rainfall in it right away. Plus 1.08545 times 1890. And I need to know the numeric value of that. Okay. So I'm hoping one of you could do that for me. And now I'm going to have the other things that are added together that will be multiplied by the rainfall level. So those are the things which are now double underlined. Okay. 168.27 minus 0.08781 times then the 1890. So I've got these two numbers shown here that I need to multiply, I guess, do the calculations on. And I'm sort of at a stalling place until you can tell me that number there. And then also this second number here. So I'm just going to go with, I'm waiting, 2047 subtracted from 1.08545 times 1890. So I'm going to try it on my calculator because that is slow. Actually, you know what? I wonder I have something written or open here already. I'm still waiting for someone to tell me the answer, but I have something that I can use as a quick tool. And I'm going to go with the negative 2047.0 plus then 1.08 1.08545 times 1890. Okay, so 4.5. Okay, so I'm going to write that down 4.50. Again, maybe this is cluttering up the screen a little bit, but y'all didn't tell me the number, so this is what you're going to get. Okay, so I've got my 4.50 as the intercept. I took my two terms that are added together, the original intercept plus the slope of year times the actual value of year when the year is 1890. And what about this second term, which we don't know exactly the value of? We've got here 168.27 minus 0.0878. I can't really see it so clearly. 0.08781 times 1890. Okay, and that seems to be 2.3091. And that's times the rainfall level. So if the year is 1890, my predicted yield, do I have a way of calculating what it would be? Yeah, that's a trend line. I'm so happy. We have a trend line. And I know the intercept and the slope, and I plugged in an 1890, and I see indeed the outcome. And so, what if it was a different year? And rather than redo everything, I'm going to erase just the parts that involve the 1890, and I'm going to plug in a different year, and I'm going to go with 1920 instead. So, erase the 1890 over here, erase the 1890 there, erase the 1890 there. Right there, right there. And then I'll have to, of course, erase this term as well, the last one. We'll have to sort of redo those calcs ourselves. But I'm going to plug in now in a different color. Let's go with blue for 1920. So we've got 1920, 1920, and 1920 in that spot as well. And so if the year is 1920, we have a new intercept and a slope. And let's go with the new slope first, because I have most of the parts entered into my calculation. Actually, let's go with the intercept first. The 2047, you can see here, I've got this, maybe I'll move it down here. See how I've got the 2047 plus 1.08545 times 1920. I have to replace the 1890 with a 1920 here. And I've got a 37. My gosh, that's a different intercept. That's equal to 37.06 plus then, well, let's find then how things would change the slope. If here's our impact on the slope. The original slope was the 168, but then it's going downwards for each additional year. So the slope should be narrower or negative. Actually, negative. Okay, that's even interesting. Negative 0.3252 plus a negative 0.3252 times then year. So what we have is a different trend line for each of the two different years. And you're thinking, oh, Actually, I don't know. Maybe you're excited about it. I am sort of pleased with this, but does it give me the opportunity? Oh, does it give me the opportunity to sort of say, well, different years have different slopes? Yeah. And that's why we did the model with the interaction in the first place. Different years have different slopes. And so let's explore this a little bit differently. You could look at what we call a profile graph separately for each of the different years. For 1890, there's an XY relationship relating X rainfall level to Y yield. For 1920, it's a different trend line. The trend line changes across the years. JMP has built in, unlike Minitab, which our authors use for analysis, JMP is a little bit better of a package in this regard. We have the ability under factor profiling to just turn on the profiler. Remember last time we just sort of said, oh, well, what if it's a this or what if it's a that? It just changes the trend line. And this profiler is super helpful. I'm going to raise it up higher on the screen and make it bigger so I can see more easily. Basically, here is the rainfall relationship with yield. We're showing you here the average rainfall level, but I'm saying this is corresponding to like 1908.5. What if it's early on in the data set, like 1890? We calculated the slope and the intercept of this line, and you have an estimated yield, even a range of values for the plausible average yield. You're 95% sure that the average yield is in the range 27.3 to 31.5 bushels per acre. That's not a range of values for the individual yields, but we're 95% sure that the average is in that range. And that's 1890. You could choose then, like we said, well, what if it was 1920? We dragged it all the way over here, and we saw the slope was slightly negative. And so I'm saying this profiler, the prediction profiler, allows me to nicely understand the real XY trend, X being rainfall and Y being yield, as a function of a different X variable. We're effectively saying we're fitting a multitude of regressions. Actually, I shouldn't say it that way. What we're fitting is a regression with three X's. One of the X's is effectively dictating the slope for the X we care about. So I'm sort of thinking a couple things. One is, why does the slope get less? And B, why does the intercept seem to climb? Well, I guess if the slope gets left and we're trying to sort of go through the bulk of where the data values are, the intercept would have to climb. Okay. But let's talk it through from an ag history point of view. If it's 1890 and you probably don't irrigate your crop, then you pray for rain. If you have more rain, you get a higher yield. Okay, cool. I'm happy with that. If it's 1920 and you are irrigating, here's the downside. Or even 1930 and you're irrigating, here's the downside. They didn't really have the weather channel yet. They didn't have predictions of rainfall in a week or two. The Farmer's Almanac said, oh, in March it will be dry, and they published that the previous September. You don't really have a lot of ability to sort of forecast rain. And so if it's been dry for a week, and your corn is looking pretty, dry, you'd say, yeah, let's irrigate. And you irrigate, and then 2 days later, you get a dump of rain that had you known it was coming, you wouldn't have irrigated. It's possible to maybe put too much water on the corn. Too much water will be harmful for the plants. Effectively, they aren't able to breathe if they're sitting in standing water. You're slowly killing the plants. So too much rain we know is bad. Not enough rain we know is bad. And if you don't know that there is rain coming in a short period of time, you're going to say, well, let's irrigate. And that's probably No, I shouldn't say probably. That's quite possibly what was happening later on, where if there was too much rainfall, like 16 inches, you would have already irrigated. Then you get this dump, and it really has a massive negative impact on the plants. You thought you were doing the right thing, and you ended up doing the wrong thing. Okay, so that's a story. Any questions about that story? Okay. So what I'd love to do then is to note here, we can also use, well, okay, define one term. I will say if you don't have interactions, you say that the model is additive. So if I say additive model, you think, oh, no interactions. If I say, I don't believe, if I don't believe an additive model is appropriate, I'm saying I think the interaction is a good idea. You literally could include the interaction to test for additivity. And if the null hypothesis of no interaction is not rejected, an additive model is a reasonable thing to believe. However, if the null hypothesis of no interaction is rejected, it says you need the interaction. You need a non-additive model. An X variable could be actually interacted with itself, and that's sort of goofy, but if you think about it, and I'll show you the graph here, maybe let's click into this here with Graph Builder. If I were to plot rainfall along the x-axis and yield along the y-axis, and I'm going to go with this curve, and I'm going to sort of like straighten it out a little bit, but not make it perfectly straight. Does it look as though for low rainfall levels, there's one slope, but for higher rainfall levels, there's a different slope? Yeah. Does the slope of rainfall seem to depend on the actual rainfall level? Steeper and then shallower? Yeah. We would say in a situation like this, a self-interaction might be a way of dealing with that. Effectively, we could fit a quadratic. We could have a curved relationship between X, rainfall, and then Y, corn yield. The model I fit could be literally something that's like a linear plus something that's a quadratic. Let's go ahead and try that with JMP with these data. And I'm gonna sort of get rid of that and this and use JMP fit model. Like always, we seem to fit model. I'm gonna sort of just start fresh. Yield is allowed to depend on rainfall. Cool. And then I could take rainfall, and could I cross it? Haha, I can. Or here's a fun one. Yeah. If I start fresh, I could say highlight rainfall, and notice it says degree 2. I could say polynomial 2 degree 2. That will fit the linear and the quadratic term. If I said polynomial 2 degree of 3, it would fit even rainfall cubed. But I don't want to go there. I'm just saying rainfall and rainfall squared, that's what we want in our model. We're fitting a linear term and a cubic term, or a quadratic term, I apologize. And here's the trend we fit. Okay. Again, when JMP sees, oh, I could show you a plot of the fitted line, I will do my best. And my R squared is like, oh, 30%, not too bad. And overall, does at least one of the terms matter? Yes, it does. How about then the parameter estimates? Let's go with effects test first. Oh, no, I don't like effects tests. Here's why. Let's interpret the rainfall p-value. If you have a model with rainfall squared in it, does adding rainfall in as well help us? And the answer is yes. But that sounds like a really pretty awkward statement. I guess in a mathematical sense, and we could talk about this more at a different point in time in office hours if you like. Y'all remember algebra from high school? Yeah, literally a model with just rainfall squared in it, but if it did not have rainfall at all, It's going to fit a parabola, and a parabola would be fit with 0 as the center. Whereas here we have a non-zero center. It's like close to 12 and a half or 13. This rainfall p-value is literally tackling the question, is the curvature, is the bottoming out or the top of the parabola that fits best, is it at an x of 0 or not? Algebraically, it's a question which makes sense, but I'm thinking I don't like it. I would rather use sequential. Let's talk about why sequential helps. The first question is, does rainfall do better than nothing? Yeah, there's a trend. A linear trend is better than no trend at all. And if you already had a linear trend, does adding in the curvature term help you as well? And the answer is yes. So we can fit a quadratic model as well. We could even fit in a model which has like more terms than just that. But let's talk about one last thing, and that is called the order of a model. The order of a model literally is the sum of, no, the highest of the sum of the powers of the, okay, what the hell? Okay, if I have a just one x variable, it would be a first order model. If I have two single x variables, like rainfall and year by themselves, it's like rainfall to the first power, year to the first power, yeah? Indeed, that's a first order model. But what if I had rainfall and year, and then rainfall times year, a first order term, because the power of rainfall is 1. The power of year here is 1. But here I have rainfall to the first power, power of 1, and year to the first power, 1 and 1. Okay, the sum of the powers of a term. This third term here has a power of 1 times a power of 1. That would be 1 plus 1 is 2. Second order model. We're not fitting just a line or a plane. We're bending the plane. We're making it a second order term. Rainfall, power of 1. Rainfall squared, well, that's clearly a power of 2. That would be the largest of those, 1 and 2. The larger of that is 2. A second order a quadratic model would be second order. Heck, if I even had rainfall year, rainfall by year, that interaction gets me a second order term. And rainfall squared is another second order term. 2 second order terms. The model is still a second order model. And you can make the model more and more complex if you want. The key in our book talks about this marginality of a term. Have the more complicated things listed later. Like I've got rainfall year listed after rainfall and year. Rainfall squared is listed after rainfall. More complex things would be to the right, simpler things to the left. That will allow the sequential sums of squares to literally make sense. Let's go ahead and try this fourth model here. Rainfall year interaction and the rainfall squared. Let's see if our quadratic, okay, function would still then maybe even bend that. Let's go ahead and fit that and see if we do better. So fit model. I'm going to say the yield depends on the rainfall. Boom. The year. The rainfall year interaction. So I'm sorry, that's wrong. Year is what I wanted here. Rainfall and year. And the year interaction with rainfall. Next, cross that. And then have rainfall squared. Rainfall and rainfall cross to get the rainfall squared. I click run. And the question is, do I need all of these complex terms in my model? Well, I guess you'd rather not have the complicated terms if you could avoid them. My R squared is 57%. That feels pretty good. Let's go with our sequential tests here. Sequential tests. Are you better with rainfall than nothing? Yes. Do you want a model with year as well? Yeah. Do you want the rainfall year interaction bending that plane? Yes, we do. And is there curvature in the rainfall relationship to y? Heck yeah. This model here with these 4 terms, the 2 simpling ones, and the one that bends the plane and the one that adds a bend in a different direction, sort of a quadratic, this is the right way to go. You could even consider a model with a third order term, but that's something I don't want to deal with right now. Good place to stop. The lab walks you through another data set like this where there may be an interaction. You'll check for the interaction. And if you want to keep it, if it's statistically significant, you'd say we prefer the model with the interaction. And then you're trying to, with the profiler, maybe come to terms with why the interaction would make sense. Okay, that seems to be a good place to stop for the moment. I'm going to stop the share unless one of you tells me not to. Okay, and I'm also going to stop the recording again unless someone tells me not to.